Hello, everyone, and welcome to Virtual Live at Frost Science. My name is Daniela Rihuela. I'm the Director of Educational Programs at the museum, and I'm so excited to welcome you to today's session. Today's session features Dr. Angela Colbert, our Knight Vice President of Education at the museum. Now, Angela wears a ton of hats. She works across various departments at the museum, working with community partners like universities, local and national nonprofit organizations, and various industry partners. But she also has the very big job of directing our development and delivery of all of our science content at the museum for all of our wonderful guests of all ages and backgrounds. Angela, thank you so much for coming in today.
Thank you, and thank you for that very nice introduction.
And now, Angela, I know that apart from doing all the amazing things at the museum, you have a PhD in meteorology and physical oceanography from the University of Miami's Rosenstiel School of Marine and Atmospheric Sciences. So, AKA, you're also a hurricane expert. So, tell us, how did you end up working in the museum setting with such a rich background, and what are you going to highlight for us today?
Thank you, Daniela. So I ended up working in a museum completely by chance. When I was in graduate school, they were looking to develop an exhibit all about hurricanes, actually. And so that's where I got my start at the museum, and I've worked my way up since then. So it's a very nice success story. At least I hope I'm successful.
Very, very successful.
And so today I really want to talk about a really large passion of mine, which is hurricanes. I've been fascinated about hurricanes since I was a little kid. I was the crazy one that, parents hate, that I ran outside during the storms instead of inside. And I've always been fascinated by weather, and hurricanes, living and growing up in Florida, were always just one of the top things for me to really be interested in. And so I was very excited that I was able to pursue and actually receive a PhD studying hurricanes. So we're going to talk about hurricane science a little bit, and we're going to talk also about some of my research from way back when. So I'm very excited to share all of that with you today.
Perfect.
So I'm going to go ahead and share my screen so everyone can see. Okay. So the storm was what I titled this talk, because that is the center of a hurricane. It is also where it is the calmest part of a hurricane. So it's really fascinating, a lot of the science that happens behind it and the physics that go into creating it. So let's talk a little bit about what's been going on with hurricanes over these last few years, because there's been quite a few ones that have made quite a name for themselves. So first, we had Hurricane Harvey back in 2017. Hurricane Harvey was a Category 4 hurricane at landfall. It actually had 60.58 inches of rain at its peak location, and many places saw over 40 inches of rain throughout the Texas coastline and in Houston where it hit. This resulted in $125 billion worth of damage. But that wasn't all that season. We also had Hurricane Irma, which was much more near and dear to all of us who live in Florida. That one actually was a Category 5 at its peak with 180-mile-per-hour winds. Luckily, by the time it actually made landfall in Florida, it was a Category 4 or 3, depending on where you were. And that one, though, resulted in $77.16 billion worth of damage. Then there was Hurricane Maria in 2017. So 2017 was just one of those crazy years for hurricanes that really left a memorable impact for a lot of people. Hurricane Maria was a Category 5 at landfall in Puerto Rico, and it just created complete devastation. It resulted in $91.61 billion, and it had a maximum sustained wind speed of 175 miles per hour at landfall. This is just what you would imagine to be one of the worst case scenarios to happen. Then 2018 happened. A lot of people remember 2017. They were very nervous for what happened. And we got Hurricane Michael up in the Florida Panhandle. Hurricane Michael originally was a Category 4 at landfall. And based on the damage and some other information that they received, they actually upped it to a Category 5 at landfall with 160 mile per hour winds. And this one resulted in $25.1 billion worth of damage. So all of these storms aren't just creating, small amounts of damage, but they're really creating large billions and billions and billions of dollars worth of damage. So what's going on? Why is this happening? What goes into hurricanes that's making them so strong? Are they changing? What are the patterns? So that's what we're going to explore a little bit today. And so with Hurricane Dorian in 2019, this one, it was the most recent one that happened to us. I know a lot of us had a really good scare with this one here in Miami, and we were very nervous for quite a few days. And as you can see, it just grew into this behemoth of a hurricane. And it ended up being a Category 5 at landfall with 185 mile per hour maximum sustained winds. Now that's tied for the record strongest winds ever recorded at landfall, with one from 1935 that actually hit the Florida Keys on Labor Day. So that one, it has a less of a dollar amount in damage, but the devastation was just utterly heartbreaking for the Bahamas. And one of the really interesting things, and I'll get to this a little more later that you'll note, is it just stalled out over the Bahamas. And so we're going to talk about that a little later when we look at the future of where hurricanes are going as well. Yes, Danielle.
Hey, Angela. So you're totally right. I live in Florida and Miami, of course, and I remember very vividly all of these very gigantic, enormous storms. It was terrifying in many cases. But let's go back a little bit to basics. So what do you need in order for a hurricane to form?
That's a really great question, and one I get asked all the time. So how do these even start? So what you need in order for a hurricane, I like to call it the ingredients needed for a hurricane, is the first thing you need the most of is warm ocean waters. So this picture that you see here is actually a picture of the waters before Hurricane Irma. So you see all that bright red? That is great for growing a hurricane. So hurricanes need warm ocean waters. They also need really moist, humid air. So when you go outside and you get all sticky from the sweat and you just feel like you need a shower 5 minutes after going outside, which is how I feel in the summer in Miami, that is also perfect for a hurricane. That's what a hurricane needs. So lots of warm ocean waters, really moist, humid air. And then they also need this thing called low vertical wind shear. Now we'll talk a little bit more about what that is, because that's a whole bunch of jargon of I don't even know what's going on. So we'll talk about what that is. And the last thing that they need is something called a pre-existing disturbance. So this basically means a thunderstorm, a collection of thunderstorms. They need something to form in order to grow off of it. So you often probably have heard of the Cape Verde storms. These are the ones that come off the coast of Africa. So they need some kind of pre-existing clouds or storm in order to start the whole process and for it to grow into a hurricane. So vertical wind shear, and I mentioned this, but let's talk a little bit for a second about what it actually is. So vertical wind shear is, we're talking about winds in all the levels of the atmosphere. So there's many different levels of winds in the atmosphere. You have winds at the surface, you have them in the low level, so a little bit above you, and then you have these mid-level winds, and then you have these upper level winds. And so the winds can change both in strength and direction as you go up in the atmosphere. What a hurricane needs is weak shear or low vertical wind shear. So that means there's not much change in those wind fields as you go up in the atmosphere. So they're all blowing in the same direction and all at around the same speed. So that's what's really important. On the other hand, strong vertical wind shear will actually change as you go up. So it could be in speed or it could be in direction, and it doesn't allow the storm to grow up vertically, which is what a hurricane needs to really start forming. Do we have a question?
Yes. So you mentioned the ingredients to a hurricane. We have a question from Tammy. Do you need all four for a hurricane to form?
You do. So you need all four in order for it to start to form, because if you have higher vertical wind shear, the storm's not going to be able to really grow and form, because like I mentioned, it's going to cut off the top. If you have colder waters, it won't conduct the heat and rising of those surface warm rising air that it needs as well, and it won't be as moist, the airfield. So if you have dry Saharan dust that comes through sometimes, that also hampers the storm from being able to actually form. So you do need all four in order for a storm to form. That's a great question. So after vertical wind shear, we can take a look now at where these storms are actually forming. So hurricanes happen all throughout the world. They're actually called different things depending on where you are in the world. So over in the North Atlantic Basin, they're called hurricanes, and in the East Pacific Basin as well. So over here, they're called hurricanes. Here, they're called hurricanes. Over here, you've probably heard the terms typhoons and super typhoons. Same thing, they're just called something else. And down here in the Indian Ocean and in Australia, they're actually called tropical cyclones. So their formal name is tropical cyclones that we use as scientists to describe all of the different levels. But here, what you're more familiar with hearing is probably a tropical depression, a tropical storm, and then hurricanes and major hurricanes. So that's the terminology we use. But as you can see, hurricanes form through pretty much all of the world and can impact a variety of coastlines. And with that, this, in case you're wondering, is only from 1985 to 2005. So this is every track of a hurricane or tropical storm from 1985 to 2005. So it's only 20 years of storms in this picture. So that's just crazy to show you the amount of storms that we get over time.
Yeah, and I noticed also, Angela, that there's certain areas around this map where there's more trajectories. Why is that?
That is a really great question. So one of the questions we also often get are, why are there no hurricanes in some locations? So we deal with them a lot here in Florida, but as you can see on this map over here in this East Southern Pacific, there's not really any. There seems to be this gap here that's occurring. Up here, you don't really see them. So why aren't they forming in these locations? So one of the key things, as we mentioned, is they need warm surface ocean waters. So if we look at sea surface temperatures, we're looking at March for the southern hemisphere storms and September for the northern hemisphere storms. So oceans are a little bit delayed in their temperature. So although the sun's strongest in July, it actually isn't until September that the oceans are the warmest. So that's in part why hurricane season peaks in September for us here in Miami. So what you'll see is that you'll see these really warm surface ocean waters wherever a lot of these storms form. So you see them here in the tropics and in other places when it's that respective hurricane season. So you need those. But in the areas, if you look, that don't get as many hurricanes, you'll start to see lighter sea surface temperature colors. So you'll notice that they're a lot lighter. They don't have, meaning that they're a bit colder in terms of their temperatures. And so hurricanes need that warm ocean water. So if it's colder water, they won't form that. The other thing that's really important is this thing called the Coriolis effect. So what is the Coriolis effect? So the Earth is actually on an axis. So now if you go into space, this axis is tilted, but just go with me here that we're just going to put it straight up and down because this has been corrected for Earth's tilt. So you have this axis, imaginary axis, that goes through the center of the Earth. And the Earth rotates from west to east. This is why the sun rises in the east and sets in the west for us. And so that rotation, along with the fact that the Earth is a sphere, so meaning at the equator, the Earth is bigger, it's wider, than at either of the poles, north or south. Because of these two things, you get this phenomenon known as the Coriolis effect, which actually causes us to have the rotation in hurricanes. So with that, what happens is a hurricane has a low pressure center. That's the eye. Air's going down. That's why it's the clearest, calmest air that you'll see. And it's surrounded by higher pressure than that low pressure center. So all the high pressure wants to travel to the low pressure. So it starts to travel in towards that center. Now, if the Earth wasn't spherical and it didn't spin and you didn't have the Coriolis effects, you wouldn't get this swirling pattern that's so familiar, but you would still get low pressure, high pressure to go to low pressure. But instead, because the Earth is a sphere and because it's rotating, you get a deflection of that. So this is an apparent force that occurs. And in the northern hemisphere, you get a deflection to the right. And so that means that your storms now move counterclockwise in the northern hemisphere. Now, if you're in the southern hemisphere, it's the opposite. The same phenomenon happens, but things get deflected to the left. And because of that, you get a clockwise rotation in the southern hemisphere. So yes, hurricanes actually do rotate the other way in the southern hemisphere. So if you want to watch hurricanes off the coast of Australia, you will see that they do in fact spin clockwise. So with that, this Coriolis effect, it transitions to zero, or it has a zero value as it goes to the equator because it's switching directions, right? So in the northern hemisphere, it's one way and it's strongest at the poles, and in the southern hemisphere, it's the other way and strongest down in the south pole. And so because of that, at the equator, the Coriolis effect actually goes to zero. And without this ability to create this spin in the storm, you can't form the storm. So between these two things is why you don't get hurricanes in some locations. So along the equator, it's not because there isn't warm water. There's plenty of warm water there. But because you can't get the spin of the storm, hurricanes can't actually form there. And then in these other areas that you see, it's because of the colder sea surface temperatures.
Hey, Angela, we have a question from Jorge. What happens if we have a hurricane that is higher than a Category 5, and is that even possible?
So that's a really great question, Jorge. So currently, the way that our Saffir-Simpson wind scale lists hurricanes, how you're familiar with hurricanes, a Category 5 is any hurricane that has 157 mile per hour winds or higher. So there is no such thing as a Category 6. Now, I'm sure you've probably seen some of the questions going out there based on, like we mentioned, Hurricane Dorian and some of these other really strong storms of should there be a Category 6. Currently, there's not, though, and there is no plans that I'm aware of, at least, to create an additional category because these wind scales are based on damage. So once you get above 157 mile per hour winds, the damage is just catastrophic. And there currently is no level beyond catastrophic, unfortunately.
Wow, that sounds a bit scary.
Yeah,
While we're on the talk about like very large hurricanes, we have a question from Zoe, who's in 3rd grade. And Zoe is asking, how large could a hurricane possibly become? And is there some sort of limiting factor to the size or strength of a hurricane?
So we'll talk about strength in a little bit. and that one's a little more grim. But in terms of size, these can get huge. So there is somewhat of a limit. A lot of the storm's size depends on the conditions that it's around, how warm the water is, how it's able to grow something called convection. So convection is all those thunderstorms and rain bands and clouds that you see that form around a hurricane. And so if it's able to form a lot of those, the storm will grow in size. Now, if a storm's moving really fast, generally they don't grow as large. But when they slow down in their speed and their forward motion, they tend to grow because they're over warmer water and this upward motion that you need to create all these rainstorms and crazy winds and all of that that are a part of a hurricane actually come through, and so they can get really big. I mean, they've been, as you saw with the picture of Irma, it was the entire state of Florida was covered at one point by the hurricane. So they can get quite large in size. Now, there are limits in terms of how large they can get, because generally they'll run into something. So they'll either hit land or they'll travel over cold water and start weakening. So those are more of the limiting factors in terms of the size of the storm that you're going to see. Over something else, if you had just like a pure ocean and no land and no interactions, I haven't gotten to do those studies, but I'm sure it'd be pretty cool. I'm sure you could get some really big storms that form, but because it will eventually interact with land or go over cold water or have some dry air come through or something that will weaken it, that will be what limits its size and how large it ends up getting. These are really great questions, so please keep them coming. I love this. So let's talk a little bit now about what steers hurricanes. So why hurricanes go where they go. So this is actually showing you clouds from 2005, which was a very active hurricane season. I believe there was 28 storms on record that year, which is the highest in our database. So this is the Atlantic Ocean over here. So what you'll see is winds in this part right here along the equator and a little bit north and south in the tropics, they go in this direction towards the west. And so we call those trade winds or easterlies. Now, when you go up higher, where most of the US is, these are known as the mid-latitudes. And here what you see is a lot of these storms and these fronts and all of these weather patterns are going from west to east. So as you know, a lot of cold fronts come from the west coast over to the east coast. And so those are known as westerlies. And then when you get up to the poles, you won't be able to see this because of maps, it goes back to easterlies. So this kind of motion that occurs and these winds are really what steers hurricanes. So when they're looking at which direction a storm's gonna go, it matters if a front's moving through, it matters a lot in what we call the mid-level winds. So this is the mid-level part of that vertical atmosphere we were talking about. Now, all parts matter, but the middle part is the one that primarily dominates where these are going to go and how these storms travel. So with that, along with this rotation in the earth that causes them to spin and turn, you get how hurricanes travel at a very basic level. So then the question that I get asked, and this is the second part of Zoe's question, is what conditions are needed for a storm to intensify? So this shouldn't be too surprising, and this should actually feel like I already did this slide, because it's very similar to what you need to form a hurricane in order to understand what you need for a hurricane to intensify and grow. So you need warm ocean waters. Just like you need it to form, that is one of the key things you need for it to intensify. So this picture here is actually the Gulf right before Hurricane Harvey was going to come through. So you see all these super warm waters here. Well, the hurricane was going to go right over those, which would help it intensify. You need that moist, humid air. So this is very, very important in order to get these storms to continue with the rain and the convection and all those thunderstorms that I was talking about. And then you need that low vertical wind shear. So if any of these three things happen, a storm is going to begin to weaken. But if all of these conditions are present, then it will really grow. So ahead of Hurricane Dorian, it had warm ocean waters, it had moist air, and it had low vertical wind shear, which was all a recipe for Hurricane Dorian to grow into the monster that it became.
Angela, we remember how big Hurricane Dorian was, and we are all wondering, A, are storms going to get worse? And I have a question from Tammy asking, is there any way to predict how many storms there will be in a year? And if so, how do you do it?
Okay, so Tammy, we will come back to your question in a little bit. There is a way that they predict. It's based a lot on statistical models that they run, and they're looking at a lot of the conditions that we're gonna kind of talk through here in a second. And so we'll come back to that one at the end if that's okay with you. So to answer your other question, are hurricanes getting worse? This is one of the top questions that's being researched by scientists right now. They really want to know the answer to this question because it has such a large impact on human lives. We all care about this. We want to know what's going on with hurricanes and what impacts may be and what they may be like years from now into the future, even this year here in 2020 and truly beyond. So this question really gets at the heart of what I did as a research student back in the day, and what motivated me behind really studying these phenomena. So one key thing to note is that the oceans are warming. So we're gonna watch through this. This is showing you the year span of 5-year averages of ocean sea surface temperatures. And what you're gonna see is that all of a sudden it's gonna turn very bright red. It's not equally red. Some parts are still cooler, some parts are warmer. But what you'll see is over the past 100 years that the oceans have gotten warmer overall. So what does that mean for hurricanes? Well, hurricanes love warm ocean waters. So that's not good news for hurricanes in terms of their development. But this also means that a phenomenon known as El Niño is more likely to occur. So the reason why I'm bringing up El Niño is because El Niño is very important in terms of predicting what a hurricane season is going to be like in terms of the number of hurricanes that are going to form. So what an El Niño is it's what is known as a sea surface temperature anomaly. So what that means is it's this change in sea surface temperature when you look over all these sorts of averages that occurs, and you get what you see here, which is this red warming along the equatorial Pacific Ocean. And so when this happens, this is what's known as an El Niño. Now, El Niño has a huge impact. It affects the weather that we see over winter, whether it's wet or drier. It affects droughts out in the western US, and it actually affects weather patterns all over the entire globe. Crazy, I know. But this one is a very important factor in terms of hurricanes. So what you see here, this is a normal one, so you have some variability, but when you start seeing these big changes in temperatures, that's an El Niño. And so the reason why I bring this up is because El Niño matters in terms of hurricane tracks and where storms go, not just frequency. So what we know about with El Niño is that during El Niño years, you get less hurricanes. This has been known for a while, and the reason for that is because generally during El Niño years, all the way over here in the Atlantic Ocean, we actually have higher vertical wind shear. So that crazy term that I said earlier, you get higher vertical wind shear during El Niño years because it's impacting the global weather. And so you get less storms that can form. So with that, there's also 2 other modes. So we have La Niña, which is kind of like the flip. So it's basically when you see this cold anomaly for La Niña. And then there's neutral, which means it's not overly warm or it's not overly cold in that equatorial time. And so what you'll see here also for La Nina and neutral is you tend to have about the same kind of number of storms for those 2 years. So you really only see the drop off in El Nino. And so you have this less hurricanes during El Nino, but the ones that do form tend to recurve into the open ocean more. So what my research looked at was really tracks and where hurricanes would travel due to changes in climate. And so with that, what I found was that during El Nino, you see this change of these storms actually going and recurving more into the open ocean than during La Ninas or neutral years.
Angela, I know that all of us were so fascinated by that previous slide that you showed about the ocean waters. So we have a question. It's actually a continuation of a question from Zoe from 3rd grade. Could we possibly have a superstorm in the future as global temperatures rise, especially as ocean temperatures rise?
So superstorm, that's hard to define what it is. I could say that Hurricane Dorian was already a superstorm. So, you know, with that, it's possible. So the warmer the waters get, the less there's vertical wind shear, the less there's these other barriers in place. Also with climate change and global warming, it's generally thought that the earth is kind of more moist, more humid in a lot of these tropical areas where hurricanes would grow. And so with that, there's a lot less barriers in place to really, you know, reduce the intensity and reduce the size. Now in the Western Pacific, the storms have actually gotten higher than 185 mile per hour sustained winds because they have less of those deterrents over there. So they've already seen storms that have, you know, I believe, don't quote me on this because I'm going off of memory, but you know, over 200 mile per hour winds sustained.
Wow.
For some of their hurricanes. So it's possible for them to get stronger. How strong they're going to get, we don't fully know. Because generally, like I said, there are those things that will limit it. It will run into land. Some dry air will come in. Something will help limit it. Or, you know, it could even just move very slowly and suck up all that nice warm ocean water, and then it doesn't have it anymore. So it's going to start weaken. So there are some limiting factors that will hopefully keep them from getting to be a crazy, crazy superstorm.
And while we're speaking about superstorms, very interesting. Jorge asked, can 2 storms or hurricanes join to form a bigger storm?
So there is an effect that happens where if 2 hurricanes get too close together, they do this kind of dance. It doesn't happen very often here in the North Atlantic. It has happened over in the Western Pacific a few times, and you see them do this kind of dance where they kind of circle around each other. They don't necessarily reform as a larger storm, but usually one of them sucks up the energy from the other one. So they do form in that way. But I wouldn't say that they form one ginormous, huge storm when that happens, thankfully. But the energy can't sustain both usually when they're that close together.
And Cindy had a question. You've mentioned about limiting factors. Can hurricanes form on land?
They cannot. So weird things have happened where hurricanes have actually strengthened a little when they went over the Everglades. So that's where sometimes people get this question. But that happened because the Everglades is a swamp. So it has a lot of water associated with it. So it's kind of land, but it's also swampy, marshy areas, and it wasn't a huge strengthening. So no, hurricanes can't form over land.
And one more question from Elijah and Emmerich in 3rd grade. They're asking, are hurricanes going to move more quickly due to the warm ocean waters? And how will this impact their ability to grow stronger?
Right. So that's a really great question, guys. So there was a paper that literally just came out like 2 or 3 days ago that actually show the opposite. So remember I mentioned with Hurricane Dorian that Dorian actually slowed down, it stalled out, and it stopped moving more or less right when it was over the Bahamas, which is the ultimate worst case scenario to have happened for the Bahamas. And that is because what we're seeing instead, yes, the waters are warming, but we're starting to see these collapses in this mid-level wind. So when we talked a little bit ago about this mid-level wind being very important for steering where hurricanes go, we're actually seeing that sometimes without a front moving through or things like that, to get the storm to move, there's this collapse that's happening. This is what happened with Dorian, and it stalls and it just sits there. And so what this paper found was actually that storms may be slowing down in their forward speed instead of speeding up, which means that if that happens near land, that they're going to be interacting with that land for a much longer time period than if it was a quick moving storm. So back in 2004, there was Hurricane Charlie that moved very quickly across the state of Florida. It came up along the Gulf side of Florida and went across and through Orlando. And it moved very quickly. It was across the whole state in a very quick amount of time, and the storm was small. Now, when these storms slow down, they tend to grow much larger as well. So the impacts will be felt in a much larger way. So that's some of the latest research that's being done. So this is such a great question because this is what scientists are looking at. So I love all these questions. I love all these ideas. Please keep them coming. And let's talk a little bit more about back to the question of, are hurricanes getting worse? So if we have more of these El Niños that are occurring, and if we have, which means less hurricanes, right? So more El Niños meant less hurricanes for us here in the North Atlantic. But the big but is that they could be more intense. So this could be in terms of, like I mentioned for them, it could be in terms of rainfall, it could be in terms of wind speed, it could be in terms of size and the kind of time length of their impact. So the current consensus is that there will be less hurricanes, but they'll be more intense. Now, this is still somewhat debated, as all science is, because it's very hard to predict the future. So if they're more intense, though, the next question naturally is, where are they going, though? Because if it's super intense and it's out in the middle of the ocean and it's not affecting anyone, that's not as bad as if it's going to affect people on the coast. So with that in mind, this is a picture of actually before Hurricane Michael came ashore in the Panhandle, the Florida Panhandle, sorry. My brain stopped there for a second. Along the Florida Panhandle. And so this was Michael's strongest hit before, and then this is it after. So I'll do that again, just so you can see it. So this is before, and then this is after. So with these storms getting more intense, if they're actually impacting land, this is real consequences for people here along the coast. So one of my research questions that I looked at was, will hurricane tracks change? So I did a study and I looked out to the year 2100, which I know sounds crazy, but that's what we do as climate scientists, is we look out for changes in trends and tracks well into the future. So what I found is that there was a change that I saw in the tracks. So I had less tracks that were kind of going here into the Caribbean area and the Gulf, and more that were turning out into the ocean. So this was good news. Now, this isn't very much statistically significant kind of results, and especially over here. You cannot take any of these one boxes by any means and be like, oh my gosh, this is red, this means it's horrible for Florida. No, you can't do that with these kinds of plots, as confusing as they may be. But what we look at as scientists are these kind of changes in these averages and what's going to happen. So what we saw is that storms just tended to kind of do this greater curve. So ones that kind of went more straight seemed to be curving up a little more, or ones that kind of were going along here tended to curve out into the ocean more. And so that's what we are really seeing with this picture. And so I don't want you to see this map of Florida and be like, oh no. But what we saw is that there was going to be a change in tracks, and that had to do a lot with changes in the winds due to these changes in climate as time went on. So the last question, oh, sorry. Yes.
Hey, Angela. So we have a question from Gita and Maddie regarding, as you're talking about climate change, can climate change harm a hurricane?
That's a really good question. So climate change itself is, you know, happening because of anthropogenic causes. And so what that means is that us humans, we've been pumping all this carbon dioxide, methane, other kinds of greenhouse gases into the atmosphere for a long time now. We didn't know what we were doing for a very long time, so it's, you know, no one's to blame. But what was interesting about it is that now we're really seeing some of the early research that was done in terms of how this would impact the climate, and we're starting to see those things actually happen. And so climate change can't harm a hurricane, but what it can do is it can help them grow stronger because of what happens during climate change. So with climate change, as I mentioned, the waters are warming. The ocean surface water is warming. That's check one that a hurricane likes. You're getting moister, humid air in the tropics. That's check two. And depending on where it is, the vertical wind shear, that's more variable and less understood in terms of what long-term impacts. But if we see more El Niños, then yes, that affects the vertical wind shear and we'll get less frequent storms, but the ones that will form will be more intense is the general consensus.
And a question from Maddie then, as you go on to your next slide, can we do anything to stop hurricanes? And running along with that, Tammy was asking if there was a way to control hurricanes. That actually comes from Tammy and Amelia, who's age 12.
Oh, wonderful. Yeah, so those are really great questions, right? I literally had that question myself. Is there anything we can do? So the main thing we can do, obviously, is every season you have to be prepared. So I know we're going through a lot right now all together, but we have to prepare for hurricane season. Hurricane season is June 1st officially through November 30th. Hurricane season starts a little bit earlier in the Eastern Pacific. They actually already had their first tropical depression, an early one, out in the Eastern Pacific. Their season starts in May. But for us, it's June 1st through November 30th. And so you need to have a plan in place. You need to know what you're going to do, have hurricane supplies. There's many wonderful resources available, both with Miami-Dade County Emergency Management that you can use. You can actually use one of their little apps on their website that show you which evacuation zone you're in, and you should always know that, always have a plan for your family, including pets. I always like to remind people of that, and really have something in place that you can do. So that being prepared is like the number one thing. Now, in terms of going on into the future, that takes, you know, a more collective effort. We have to work together as a whole globe in order to combat climate change. That's the only way that we're going to make a big difference. But don't let that deter you. Everyone can do something to help, whether it's things as simple as not driving your car as much. So if you can take a walk somewhere, great, you get great exercise, and you're actually helping the climate because you didn't drive the car that time. Or if there's things you can do, energy efficient light bulbs, using less energy in your house, little things like that actually do add up and make a big difference when everyone does them together. So there are things that you can do personally. And if you're really passionate about it, you can become a scientist. I'm fully on board with that. Or you can go out and actually let your politicians know that this is something you care about out and talk to them as well. So there's lots of options that you have available if you're interested in those things. But there's little things everyone can do, like I mentioned, such as just going for a walk or bike ride instead of driving a car somewhere. And those things will add up.
Angela, you mentioned hurricane season coming up. We have a question from Mia, who's 15. What if the hurricane comes before hurricane season? Can that happen?
Yes, it happens all the time, actually. Well, not all the time, but it happens quite frequently. So we often get what we call early season storms. They've happened in May quite a bit. So depending on the time in the season, they'll actually form at different parts. And so we tend to see those early storms form off or near the coast of Florida, oddly enough. And sometimes they are only subtropical. They're not a full tropical storm or hurricane that occurs. Other times they are, and it can happen if conditions are right. So I know we also had the question earlier of what this hurricane season is going to be like and how it gets predicted. So there's a few different areas that universities and organizations that actually do these pre-forecast models for what each season is going to be each year. They all have slightly different techniques, but what they're looking at are certain key factors. They're looking at what's been going on in ocean waters and what are the models saying in terms of what they're going to look like over the course of the season. Are they going to be warmer? Are they going to be colder? They look at El Nino. What's going on there? Is it going to be an El Nino? Is it going to be La Nina? Is it going to be neutral? And so they're looking at all those various aspects to help go into their predictions and statistical analysis in terms of what they can predict will be the number of storms. So with that, for hurricane season, this 2021, sorry, it sounded like I said 2021, but I meant this one for 2020. Generally, and I took just the lowest and highest numbers here of the things, they're predicting an above average season. So what that means is 16 to 22 named storms. So this could be tropical storms all the way through major hurricanes, 8 to 11 hurricanes, and 3 to 5 major hurricanes this year. So that's what this season they're looking at, and that's because the ocean waters are predicted to be a little bit warmer than they have in other years, and it's also a neutral El Nino type year, so we won't have El Nino occurring, but it's actually neutral sea surface temperatures out in the Eastern Pacific.
Wow, definitely get ready. So we've had a couple questions during your presentation that I want to bring up from America and Elijah. They were wondering, how are hurricanes named each year? How is that determined each year? Who comes up with this list of names? And we have a lot of questions about that. So who really is in charge about that?
So I love this question. So what it is there's actually this group called the World Meteorological Organization, WMO. And so they're the ones that name the hurricanes for the Atlantic and the Eastern Pacific basin. And so with that, they actually have a list of names. There's certain letters that they don't use. But they have a list of names, primarily A to Z, but like I said, there's certain letters they don't use. And they have a list that has alternating boy-girl names for each letter. So if one year, like if A was Angela, like my name, then the next year it would be an A name that's a boy's name. And so they alternate like that, as well as up and down for A, B. So the first hurricane, or the first named system for this year, is going to be Arthur. And so with that, they actually have, it goes on a 6-year cycle. So each, they come up with a list of names, and then 6 years later, they use those same set of names. But if one of those storms happens and it's a very memorable storm, the name gets retired. So it doesn't get used ever again. So there'll never be another Harvey, Irma, Maria, Michael, or Dorian, for example. And so those names get retired forever once they occur in a memorable way. Otherwise, they get reused every 6 years.
That was one of our questions, whether the names ever repeat. So
They
thank
do.
you. And we have a question from Megan's 4th grade class. They're asking, what place gets hit the most with hurricanes? And also, what is the average lifespan of a hurricane?
Two really, really great questions. So hi, everyone. So if you look over all of the history and all of the things along the entire US coastline, what you'll see is that Miami-Dade County and the Keys have the most hits from a hurricane looking across all that time. You know, that will change over time and what happens. So who knows what the future holds, but currently those South Florida is the record holder because look, we stick out in the middle of where these storms are traveling through, right? They're going either from the Caribbean or off the coastlines, and they're trying to get over to the Gulf. And Florida just is this giant peninsula that sticks out in its way. So they're going to happen a little more frequently there. Now, the second question you had was the average lifespan. So it really depends on a storm. Storms can, you know, live anywhere from, you know, 12 hours to all the way beyond to, you know, like 14, 21 days in some cases. Some of them actually go over lands and then they've come back and reformed as a depression and then started again, and it's the same storm. That happened with Hurricane Ivan in 2004. And so the lifespan can just vary greatly. So usually on average, it's about, I would say, around 10 to 14 days.
Thank you. And we also have a question. Do you know by any chance when was or what was the largest hurricane that we have had? It's a question by Mia.
Largest in terms of size, and by we you mean Miami or just the basin, or who knows?
Largest hurricane ever.
We'll go with it. So, I mean, Dorian was a pretty big one. There's been a lot of really big ones recently. Florence was a really large one. Katrina was huge. It took up the entire Gulf pretty much at one point. I'm not sure of that record holder. I would have to look that up myself, but I know there's been plenty of very large storms in recent history. So that's a really interesting, great question that I don't actually know the answer to. So thank you for something
to research for sure. And just a little bit more, a lot of people have questions around intensities and speed of hurricanes. So American Elijah were asking, how is the speed of a hurricane determined? And Lisa was asking, who created the intensity scale?
So two really great questions. So the intensity scale was created by these two guys named Saffer and Simpson. That's why it's called the Saffer-Simpson wind scale. So there were two scientists that were studying this, and they came up with it. And like I said, they based it on damage that they were seeing. So it's really based on what they saw as damage. The wind speeds are really weird in it because it was done in miles per hour. Or we view it as miles per hour, but it was actually done in a metric system. So when you look at it in knots, it's much more clean in terms of the values that occur for the changes in category. But when you convert that over to miles per hour, you get these really weird numbers like 157 miles per hour, which is very odd. And when they're actually making their forecasts, they'll generally only do it by actual levels of 5. So they'll say like 155 or 160. It's very hard for them to measure with that accuracy beyond that 5 mile per hour. So the other question, you know, with intensity, so they actually measure it, very interesting. So there's these very cool people, very cool scientists that fly into hurricanes, known as the hurricane hunters for NOAA. There's also the Air Force that goes and flies into these storms, and they've been doing this. They started kind of in the 1940s and then did it a little bit more in the 1950s on a regular basis. And so they'll actually go and fly into storms, and they drop these things called dropsons. And so what those are these little instruments. They're not this little, they're large. But they drop these little instruments out of the plane while flying in the middle of the storm, because these people are that crazy. They're literally flying through the storm. You should check out their videos. You can. It's very fun to watch. And so they go flying through them, and they drop these, and these take measurements that they send back to the plane about the wind speeds. And that's how they detect a lot of these wind speeds when they're making these measurements before the storms get to land. Once they get to land, we have our own instruments on land. So that's how they're actually measuring some of these intensities, which is pretty cool.
It's really cool. Now, it's my understanding, have you ever flown into a storm?
Oh, yeah. No, so I don't have the stomach for that. So it's very turbulent. So I've talked to a lot of people who have. They're wonderful people that do this work, and they fly into them, and it is a very turbulent flight, but you're with like the best pilots in the entire world. So it's like almost one of the safest flights you can do, as crazy as that sounds. But it would not end well for me, no. So generally speaking, I have not flown into a hurricane. I thought I really wanted to as a kid, and then I realized maybe not as an adult.
And you mentioned a little bit of the tools. Lucas is 6 years old, was asking, are there any other tools that scientists use to measure hurricanes?
So we use a lot of tools to measure hurricanes. Satellites is one of the largest ones. So our records started becoming really much more reliable in the 1970s, when satellites actually went up into orbit. And recently, just a few years ago, or a couple of years ago, we had our latest weather satellite, the GOES 16, that got launched, and it's a geospatial stationary satellite. So it watches and rotates with the Earth, and it keeps a constant eye on the North Atlantic Ocean. And so this is invaluable of a resource to scientists. It has all this equipment on it to measure rain and wind, and look through clouds, and see what's happening in different areas. And so we can have this constant view. And so it's a really valuable tool. We also use modeling a ton. So being a meteorologist, it's may surprise people, but it's a ton of math and science. And that's really cool, because you're learning about how the Earth moves and a lot of these really cool dynamics that occur. And so you get to use a lot of math, a lot of physics to understand, and sometimes some chemistry too, in terms of like how the atmosphere is, what it's made of, and things like that. And so it's very cool things that you get to see. And with that, you get to really kind of experience a lot of these cool tools. And they're collecting data from things even as simple as weather balloons. So we've actually been doing weather balloons for years and years and years and years. And that's our longest weather data, is actually collected from weather balloons, which is super cool. And so they launch them daily up into the atmosphere to get all this data, and that goes into the models that they then can use to predict what's going to happen based on physics and all this other stuff. So there's tons. There's so many tools.
Scientists are so cool. And 2 more questions.
Sure.
So you talked about models, and earlier also in some of your slides, we saw some trajectories. So Jorge was asking, why do American and European trajectory predictions are so different from one another? And I'll ask my last question.
Okay. So that's a great question. So you'll often hear about spaghetti models when you look at things. And so what spaghetti models are these different tracks based on the model. So the US has some, Europe has some, the UK has some. There's all these organizations that have these own models. And so you'll get different predictions from them because they're based on slightly, ever so slightly changes in certain physics equations and different parameters that are set in these models. And so the European one has actually done very well over the past few seasons. It's one of the best, but you can't discount the other ones, because what we're looking at when they're forming those track forecasts is actually the middle ground. And so they're looking at all those different aspects, what may be contributing to other impacts, and humans play a hugely important role, not just models, and actually putting out these forecasts and looking at them. So there's the folks at the National Hurricane Center that do all this work. They work 24 hours a day during hurricane season, and they're actually putting out these models, and they're looking at all the models, they're looking at all their other data and all their experience that they have in forecasting these to put these forecasts together. So it's very cool.
Definitely, definitely. And then last question, Maddie from age 8 was asking, when was the first hurricane, or at least when have we recorded the first hurricane?
So we used to record hurricanes in 2 ways. So our records get really bad, but they date back to like the 1850s. They're very weak back then. So we only knew if there was a hurricane if a ship basically ran into one and made it back to tell the tale, or if it went over land and actually made an impact over land. So our records aren't very strong. Like I said, pre-1970, even the ones that were further out in the Eastern Atlantic, we wouldn't know about, because how would we unless a ship like happened to go into it? So really the invention of satellites allowed us to get much stronger records and much more accurate records that occurred. And so the first hurricane actually is like way back when, before that. So that's our records of hurricanes, but it's way before then. You know, it's possible even that there was hurricanes back in the like last glacial ice age and things like that. Or when there was dinosaurs, I'm sure there was hurricanes. So it's really interesting because as long as those conditions were there, there's a reason for there to be a hurricane. So Mother Nature's awesome.
Angela, thank you so much for joining us today. I know that we are all fascinated and want to keep learning. So we have, thank you all so much for tuning in and asking your questions. Keep asking questions. Stay curious for sure. For all of you watching, we are continuing these sessions. Our next session is actually next Wednesday at 2 p.m. where we will be featuring Dr. Sarah Ballard, who is an assistant professor at the University of Florida, and she's going to be talking about exoplanets. If you'd like to support our educational programs, please visit frostscience.org/donate, and we hope to see you again very soon. Thank you.
Thank you, everyone.